Okay, so now we discuss the first two half cycles. So now we move to the second negative cycle. So this cycle I'm referring to see what happens to the circuit for the next couple of cycles. So then the input is something like that. So we have a negative input. So this capacitor remains at Vm because this during this previous cycle diode get reverse bias, and this whatever the circuit brought up is like having a high RC constant, and this capacitor uh, doesn't have a kind of a chance to discharge to the resistor we introduce because this time constant is high. So then we argued that the whatever the stored voltage across the capacitor remains as it is. So we draw this capacitor voltage in this red line. So this green line represents the output voltage across the resistor. Now we move to the third cycle. It's a kind of a second negative cycle. So then again, like in the previous scenarios, we have two options. There may be a current flow through the diode or maybe through the resistor. So now we should identify if this diode is forward or reverse, because if the diode is reverse, so we can simply conclude that there won't be any current flow through this one. If it is conductive, then diode should be forward biased. Now we'll apply Kirchhoff voltage law and found that the voltage across the diode should be zero during the second negative cycle. So for the diode, so ideal diode, we claim that VD should be greater than or equal to 0 for forward bias, and VD should be negative or less than 0 for reverse bias. But by looking at these two conditions, we can argue that for VD equals 0 scenario includes or embedded in this forward bias law. But the problem is, so this 0 is the kind of a switching point. So one can argue this as well. So one can argue VD should be greater than 0 to forward bias, and VD less than or equal to 0 to reverse bias. So these both conditions should be acceptable in certain scenarios. So this 0, VD equals 0 case is a kind of a decision making level. So it's the decision making level whether it's pushed into the forward region or reverse region. So what we can claim here is, if you refer the previous cycle, so in the previous cycle the voltage across the diode is, so it's basically reverse bias. So it's basically reverse bias. It means like, so we apply a minus 2 Vm across the diode in the previous cycle and make this diode reverse bias. Now the voltage across the diode is 0. So then we can claim that still it should be in reverse region, because if we refer to the previous states of the diode, it's definitely in reverse region. Now we reduce the voltage across the diode to 0, but it never turns on at this VD equals 0. So then still we can claim that still D is reverse bias, because previous state of the diode, D is reverse bias. Whether this diode voltage is 0, it should be still at reverse bias region because the previous state also reverse bias. So then this second negative cycle, this diode remains in reverse bias region. So then the current flow again through the resistive load. Okay. So then we have again the same RC circuit come into the picture. So then we can claim that whether you connect this R resistor to the circuit, so this capacitor never discharged because this RC constant is pretty much high. So then what would be the output across the resistor? So we have Vm to this direction, clockwise direction, and we have an input which is again equals to Vm to the anti-clockwise direction. So the net voltage across resistor would be 0. Okay. So similarly, if you consider the second positive cycle as well, you can find that diode is still reverse biased, and the only so but the circuit seems that is forward biased. How do you seems that diode is forward biased? Yeah, the argument here is, so we have a diode here during this second negative cycle. So if you apply basically Kirchhoff voltage law to find out the actual voltage appear across the diode. So we have Vm plus VOC minus Vm. So this is to the other way around, equals 0. Then VOC, open circuit voltage is 0. So we know that the actual voltage appear across the diode should be now 0. So this is the actual voltage appear across the diode. So, but ideally speaking, VD, so we have three scenarios. If VD is greater than 0, we know that definitely this should be forward. So this is again definitely it should be reverse bias. What about this boundary? So there may be a tendency like, so for example, if your voltage, if the previous states of the diode is forward biased, whether you bring the voltage to 0, it never turns to reverse. It remains at forward. If your previous state is in reverse region, whether you bring your voltage to 0, it never turns to forward. So that's normal scenario because this VD equals 0 is the boundary condition. So if you reach or if you come from this reverse region to 0, whether it's 0, we can argue that this diode voltage is not sufficient to make it really on, really forward bias. But you can stick into the equation and say that this should be 0 forward bias, but it's something like that. So your voltage, so if we just plot the curve, so this is the characteristic curve. So this is the characteristic of the ideal diode. So the voltage close to 0 means here. So it's basically reverse bias. So we can argue that the diode is basically in reverse region in the previous cycle. So the previous state is reverse bias. So once you reduce the voltage to 0, so that voltage is not sufficient to push this diode to forward region. If you just stick into the equations, you can argue that, but once you really argue with the previous statistics or the previous states of the diodes, so you can simply say that whether the diode voltage is 0, this diode, the voltage is not sufficient to push it to the forward region. So that's why we claim that diode should be reverse bias here. Okay, so this boundary condition Vd equals 0 case actually there, but depending on the scenario, the previous state, we can argue, yeah. So we can argue depending on the previous state. If it is forward bias, if it was in the forward region in the previous cycle, so whether your voltage is 0, you can simply argue that it should be forward bias. If it was in the forward region, whether the voltage is 0, you can still argue that this 0 voltage is not sufficient to push this diode from reverse to forward. So that argument is there. So we use that argument. So still the diode is in reverse region, then the output would be 0 because the net voltage across the resistor would be 0. So the polarity of the induced voltage across the capacitor and the source voltage is simply different, opposite. So then you can see whether you input this kind of a voltage, whether you input this kind of a voltage, minus Vm plus Vm, you will ended up with this kind of output. If you further, this is 2Vm, this is 0. If you just explain the rest of the cycles, you can see this kind of a pattern. So it means your input Vin is shifted by Vm amount. So what we observe as the output is actually we introduce a kind of a DC offset of Vm volts to the circuit. So we basically observe output as a kind of a DC offset of input, or a kind of a we shifted version of the input by a plus Vm or a Vm. So then this margin shifted to 0 and Vm shifted to 2Vm. So that's why we simply say that this is a kind of a clamper. Your input is basically clamped at Vm. Whether you have periodic signal which vary between plus Vm and minus Vm, your output would be simply clamp your input at Vm. So it means you the particular circuit basically add a DC offset of Vm to the input. So then your input is simply vary between plus Vm and minus Vm. Your output is simply vary between 2Vm and 0. So this is the simple clamper. So if you want to make it a kind of a boosted voltage, so you can use this capacitor and a reasonably high resistor to make this RC constant pretty much high. So then you can have kind of a 0 to Vm, 0 to Vm type of a periodic square wave, which is actually in a one polarity or a positive polarity. So initially your input is having this, it's a kind of a bipolar signal. So you have positives and negatives, symmetric around t-axis. But once you introduce this capacitor and a reasonably high resistor to make this time constant pretty much high, so you can have a kind of a circuit which provides the output clamp your input at Vm. You have kind of a positive voltage which basically vary in the positive domain on. So what again, like, so we can argue, so what about the average of this? This is ideally average zero signal. So because it's symmetric over the t-axis, so if you evaluate the area under this curve for the period, so the average would be 0 if it is symmetric around the t-axis. What about the average of this green signal? So So this is average is not equals to 0, because if you evaluate the area, so always the area is positive. So average is non-zero. So by using this clamper, you can have a non-zero average signal without using any element. So you just use a capacitor and store the energy of the source and use that energy to bring your output to this mod. So this is a kind of a clamping circuit. Okay, so then the example which I took in this slide set is a kind of a sinusoidal signal. So did you follow the video which I explained this scenario? If it is clear, I can simply ignore that part. Otherwise, I have to go through that again. So what about your idea? So I start with the square wave because it's easy to understand the internal mechanism. So then once it moves to the sinusoidal, so which as I discussed in the video, so we have to segment the sinusoidal also into two parts. Whether it's a negative cycle, we have this minus gradient and plus gradient regions. So we have to split it into two regions and discuss this. So if you are clear about this, how the output would be clamped for the sinusoidal, so I can simply move to the voltage multipliers. So what about your feedback? Are you clear about that? Okay. So, okay. So I'll discuss this example. So then along with this square wave input, so we have